Okay, hello everyone. Welcome to fluid mechanics class. Today we are going to briefly review the previous lecture, and we are going to continue discuss about the Bernoulli equation. Okay, so in the chapter 2 we talk about Euler's equation. So basically in the Euler's equation for in-beat flow, this is for great the partial p minus gamma for the z direction equal rho times acceleration part. This is for the Euler's equation. So here we derive for the Euler's equation, we assume that there is no shearing stress, right? Uh, so basically, because of the this equation, as you can see, the pressure is only depend on the z direction. I mean the same direction for the gravity. In the chapter 3, we are going to discuss about the Bernoulli equation, as you can see over here. So in the last lecture, we talked about how to derive the Bernoulli equation by using the Newton's second rule in a streamlined coordinate system, and also the normal to streamlined coordinate system. So I'm going to skip for the detailed parts because this is the review session. For the derivation, it is very important. Again, the very important is that the surface force, basically there is a two components. One is for the body and the other one is the surface. Okay, so here, sorry, this is a streamline. For the body streamline, uh, so for the left hand side, we just use the F equal ma, right? So here the acceleration part for the streamline we already derived in the previous page, so we know this is the result for the v times partial v divided by partial s, right? So basically for the left hand side we can get this term, and for the body part, we simply use the weight, right? And then because this is the tilted in terms of the xy direction, because we are going to use the streamlined coordinate system, so that to compensate these two different coordinate system, we use the zeta over here, the same sine zeta. So basically for the body force in a streamline, we can write down as like this. Okay, so again, so this gamma represent the specific weight. This one we are talk about in the chapter 2. So for the last term, for the surface force, we only use the pressure part. So for the pressure part, from using the Taylor series method, we can simply written as the partial ps written as like a partial p partial s divided by 2. Okay, so based on this knowledge, we can combine this force, we can written as like this. Okay, so these last three terms represent the volume, so that the surface force in a streamline we can written as like this. Okay, and for the if we combine these three terms, in that case we can written as like this, right? And then we just combine, just plug in each term, you can derive this result. Okay, so this is for the equation of motion along the streamline direction. So minus gamma times sine theta minus partial p partial s equal rho times v partial s, like this. Okay, so and also we do some integration. In that case, we can get this result. Okay. Okay, so for the special case, for the incompressible flow, the Bernoulli equation we can written as like this. The P represent pressure, rho here represent the density, V represent the velocity, and the gamma times Z. Okay, the gamma represent the specific weight. Okay, some other textbook it can written as rho rho GH. Sorry, rho GH. Okay, so for using this Bernoulli equation, there is some assumption or restriction. So it should use in a flow along a streamline. Okay, this is very important assumption. And also for the invisible flow, and also the steady flow, and also the incompressible flow. So here in this flow, when you recall the derivation part, in a surface force part, we do not consider the viscosity. Okay, so that for the Bernoulli equation, we can only use in the invisible flow. And also for the static flow, we do not consider the time. So basically our flow, it is not depend on the time, so that in that case we can call the steady flow. Okay, so if not, if flow depends on the time, in that case we can call that unsteady flow or the transient flow. Okay, and also in compressible flow in an undergraduate level, we can just assume that the density is the constant. Okay, so for the compressed flow, we usually call that our flow, it is the speed of is the larger than Mach number 0.3. In that case, we should not assume that your flow is incompressible. Okay. Okay. So here, if the flow is unsteady in the compressed flow, just because the velocity is depend on the time, so because you have the another term that this blue color, so that the derivation also change. Okay, and also because the compressor flow, this part, the density is not a constant, so that we cannot plug in the outside the integral. So you should use this equation for the unsteady compressor flow. Okay, so basically this is the generalized form, but the thing is that it is very difficult to apply this one in the analytical method, so that this one is just plus alpha. Okay. Okay, and also we derive the F equal ma normal to a streamline. So basically all the function is the same. Okay, so only difference is that we consider in a normal direction. So normal here represent this direction, so this is the streamline direction and this is the normal direction. Okay, so it's same, so we use the F equal ma, and also we consider the weight, and also we consider the net pressure force for the surface part. So if we combine three terms into one equation, in that case we can get this result. So this is called the equation of motion normal to a streamline direction. So here the gamma times cosine theta minus partial p partial n equal rho times v squared divided by r. Okay, so this is for the general style of the if you do some the integral, we can get this result. But for the special case in compressor flow, the density is the constant, so that we can put outside the integral form, right? So this is equation called the F equal ma normal to streamline. Okay, this is not the Bernoulli equation. So, but the thing is that the this equation is very also useful. So because this brown it represent the streamline, and this one represent the normal. Okay, so if you investigate this point, the red point and the blue point, to compare the difference in terms of the velocity or the pressure, in that case you can use the Bernoulli equation. But if you want to compare this green color and the orange color, so basically this is the normal to a streamline, so in that case you should use the second equation. Okay, so again, so assumption part is very important. To before you apply these two equations, you need to check your flow is a steady and inviscid and incompressible. Okay. So here's the we also talk about the example, right? Okay, I will skip it again. So for the Bernoulli equation, P plus rho times V squared divided by 2 plus gamma Z equal constant along the streamline. So I expect you guys to remember this equation for the exam. Okay, this is a little bit common sense for your engineering life. So it is good idea to memorize, even though after the exam period. So if we divide as a function of the specific weight, in that case we can written as Bernoulli equation like this, right? So as you can see, this one is to represent the height, so we called this one as a elevation head. So this is to represent the potential energy. So this first term represent, because this, as you can see, there is a pressure, so we can call the pressure head. So this is the related to the flow or the pressure energy. So we can frequently written as the Fe. And as you can see in this second term is the V squared divided by 2Z. So as you can see, there is a velocity. So we call this one as the velocity head. So it is represent the Ke, kinetic energy. Okay, so let's start today's lecture. So this is the brief review. So let's talk about the static, dynamic, and hydrostatic pressure. The kinetic and the potential energy of the fluid can be converted to flow energy and vice versa during flow, causing the pressure to change. Multiplying the Bernoulli equation, this is the Bernoulli equation, okay, by density givens. So basically here this is the Bernoulli equation, okay. You can just remove this word, sorry. Okay, so here P we represent as a static pressure, okay. So this one we call the static pressure. So basically it does not incorporate any dynamic effect. So it is not incorporate the dynamic effect. So it represents the actual thermodynamic pressure of the fluid. So basically, if you calculate like a ideal gas law, so this P represent the static pressure, not the other pressure. And the second term, we usually call the dynamic pressure, okay? So the first term represent the static, and the second term represent we call the dynamic pressure. dynamic pressure. So the reason why we called this one as a dynamic pressure is that the pressure increase when the fluid in motion is stopped isentropically. So basically this dynamic pressure is related to the velocity. So that's the reason why we call the dynamic pressure. So and also here the rho g z. So here the third term we call the hydrostatic pressure. Okay, so basically this one it is not the actual pressure. Okay, but the thing is that it is represent the level reference level selected. So so here I would like to highlight that many of you guys after this class and maybe 2 or 3 months later, many of you guys very confused which pressure you need to calculate and which pressure you need to obtain. So for example, in the next semester you are going to learn some CFD. Okay, in a CFD, if you do not understand static pressure concept and the dynamic pressure concept, in that case, uh, uh, you will fail to get the correct information. I mean the appropriate information from the your numerical result. So for example, so most of time we call the total pressure. So total pressure, usually we combine these 3 terms. Okay, this is called the total pressure. So if you want to see the effect of the static and the dynamic pressure and the hydrostatic simultaneously, in that case it is good to obtain the total pressure. But the thing is that if you want to get the actual pressure, like a static pressure, it is related to the actual thermodynamic pressure. In that case, you should not use the total pressure result. Okay, so basically the total pressure and the static pressure and dynamic pressure, it is the 3 different terminologies, are totally different. Okay, so here let's talk about the static pressure first. So it is the way to measure the static pressure would be drill. So basically here this is the pipe. Okay, and this is the pipe. Okay, here is the pipe, and then the water or the air coming from the left to the right. Okay, so if you want to measure the pressure, in that case you need to drill at the top of your pipe. Okay, and this is the idea. So basically here P1 represent this point. Okay, and for the P3, so this one represent just P3. Okay, and to compare the P1 and P3, you need to also consider this height. Okay, so this one we run in the chapter 2, right? Chapter 2. So here P3, there is a height as well. So we can written as P3 as a gamma H4 minus 3. So gamma H4 minus 3. So we can represent the P3 like this. Okay, so basically H3 minus 1 and H4 minus 3. So this one H3 minus 1 and H4 minus 3, if you combine these two heights, in the case this is the total height, right? So this will be, we can written as P1 equal gamma H. Okay, gamma H. So you can determine this static pressure at the point 1. So this is the static pressure, how we measure in the pipe system. And here we are going to talk about another pressure. It is called the stagnation pressure and the dynamic pressure. Here, as you can see, the P1, we know how to calculate is in the previous page. This is represent the gamma H. Okay, gamma H. So this this height. Okay, but the thing is, at the point 2, since 1 and 2 is the same location, so if you make a streamline, so we can connect it like this. Okay, so we can connect it P1 P2. This is streamline. So according to Bernoulli equation, so it should be P1. Oh, sorry, there is some error. Okay, so P1 plus rho v squared 2 v1 at this velocity, okay, equal P2 plus rho v2 squared divided by 2. Because the height is same, so I just removed the gamma H part, right? But the thing is, at the point 2, there is this fluid, there's no way to move, right? So this at this point, at the point 2, the velocity should be 0, okay? So that we can remove this term, okay? So that we can written as P2 equal P1 plus rho v squared divided by 2, okay? So here the velocity is 0, so that at this point we call the stagnation pressure, okay? Stagnation pressure. And P1 we run in the first page. This is the static pressure, right? And because this part, as I already mentioned in the previous page, this one is the dynamic pressure. Okay, so basically the static pressure plus the dynamic pressure represent the stagnation pressure. So you can know what is the difference between each different pressure. Okay, so here is the practical example. So here we call this character 2 as the pitot-static probe. Okay, so as I already mentioned, here we can fill with the fluid, right? So in this part, so at this point, the velocity should be 0, right? So which means that we can call the stagnation pressure. Okay, so this one represent this red color, right? And how about this point? This point represent, it is the measuring the static pressure. So because it is related to the static pressure, because in the static pressure we derive P equal gamma H, right? So because it is located at the, if you make a hole at this point, in the case it is the represented this height, right? So this one we call the static pressure. Okay, so this is the how we measure the static pressure and stagnation pressure, okay, by using pitot-static probe. So if you know the stagnation pressure and the static pressure, you can easily I mean the stagnation pressure. If you know the static pressure, in the previous page it is should be, we can summarize this equation, right? Okay, let's go back to the previous page. The stagnation pressure equal to static pressure plus dynamic pressure, right? The stagnation pressure equal to static pressure plus the dynamic pressure. So by using the pitot-static probe, you can determine stagnation pressure, this one, and the static pressure, this one. So you can determine the dynamic pressure easily, okay, by using pitot-static probe. So what does it mean? So if you go back to this slide, the dynamic pressure, it is represent the velocity, okay? So basically, by using the pitot-static probe, you can not only measure the stagnation and the static pressure, you can, based on these two information, you can get the flow velocity, because you can determine the dynamic pressure. Okay. Oh, okay. I already written in here. Okay. If you inside the pitot-static pressure, okay. So here is the stagnation point, okay, and here is the static pressure, right? So here you measure, here we can measure the static pressure, here we can measure the stagnation pressure, so we can determine the velocity, okay. So here is the example. So here, this is from the NASA. So here you can assume that the stagnation pressure equal to total pressure for this diagram, okay. So basically this is the stagnation pressure, okay. Okay, so here the most frequently the pitot-static probe is used in the airplane. So in the airplane, nowadays you can use the GPS, you can track we can measure the airplane speed. But a long time ago, it is also important to measure the pressure with the analog method, okay. So in the airplane, it used the pitot static probe, so that the airplane, we can obtain the velocity of the airplane by using this device, pitot-static probe. Okay, so there's some animation. Okay, so this red one, and here's the blue one. Okay. Okay, let's solve the example 3.6 together. Okay, so I a little bit changed the example 3.6 because in this textbook it is not written as the SI unit, so I a little bit adjust this number over here. Okay, so let's solve this example together. So please stop the video button, and then after you think about this problem by yourself, let's solve this example together. Okay, so here is the given. The airplane flies 3 to 2 kilometers per hour at the elevation 3048 meter. Okay, so basically we know the elevation. And determine the pressure at point 1 for our airplane. The pressure at the stagnation point here of the airplane point 2. The pressure difference indicated by a static probe attached to fuselage. Okay, so basically we need to determine the pressure. Okay, so before you need to to solve this example, you need to know the pressure at the 3048 meter. So unfortunately, there is no way we can determine the pressure at this height. Okay, so if you use the table or the Google, you can obtain the pressure at the 3048 meter. Okay, so I will give this pressure. So 69706 Pascal. This is at the height equals 3048 meter. Okay. So because we already know here is the stagnation point, so P2 equal P1 plus rho V squared divided by 2, right? So and also I should give another information. So this one should be given, okay? The P1 and rho at the 3048 meter is 0.905 kilogram cubic meter. Okay, so this one also you should find in the table on the textbook, or you can search in the Google. Okay, and also another information, 322 kilometer per hour. I don't like it because we want to use the sec and also meter, right? So if you convert this unit, in the case this one is we can written as 89.5 meter per second. So basically these three information should given to solve this example, right? So from now on, so P2, this is the static pressure, stagnation pressure, and the P1 is the static, and V1, this is the dynamic, right? So P1 is given as a 69706 Pascal. So you can just plug in all the value over here. So P2 equals 69706 plus 0.905. So rho here, this one is given, and V also given as the 89.5 squared divided by 2. Okay. So if you calculate, this part is 3625 Pascal. So P2 represent 73331 Pascal. So P2 minus P1 should be dynamic pressure. So this one should be 3625 Pascal. So this one should be same as this value. So this is the answer for the 3.6. So this example is quite easy if you know the pressure at the 3048 meter, and also density, and also you know how to convert the velocity unit as a kilometer per hour to meter per second. Okay, so let's talk about the application of the Bernoulli equation. So Bernoulli equation, we already mentioned, this one is the P plus rho V squared divided by 2 plus gamma times Z equal constant along the streamline. So basically between any 2 points at 1 and 2. So this is the streamline. And if you put point 1 and point 2, okay, so between any 2 points on a streamline is steady, inviscid, so basically we ignore the viscosity, and third, incompressible. In the case, we can use this 2 point with this equation. So basically P1, V1, Z1 is the information from here, okay, and here too, the pressure and velocity, Z is the information from at this point, okay. So this is the practical form of the Bernoulli equation. Okay. So let's take a break and let's continue our lecture in the next session. Thank you.